Okay, so 5.1 linear models, initial value problems. A couple things you're going to notice. These are going to be word problems that in chapter 4, those way of solving these types of word problems. You're going to use all those methods in chapter 4. So you're going to look at differential equations that look like something like what we're used to, okay? But instead of dy or dx, it's going to be over dt. So you could have like second derivative, and then you have a, b, and c are going to be coefficients. And then it's going to be equal to a function, okay? So usually what you'll also get is some initial value, and we're really going to deal with springs. So like, where is the spring after a given time, okay? And you'll have that as well. Now, the function that it equals, at first we won't use that much, but as you go along, then we'll have to go back to, I think it's 4 maybe, where you have to try to, superposition, try to match things, or you could use any of the methods really that are easiest. So this is like a driving force, this last function. They call it the forcing function. Sometimes an input. Okay, and the other thing I want to just show you real quick is in 5.11, right, we need something called Hooke's law. Okay, this is where force is equal to some constant. We call it the spring constant, and how long the spring is elongated. So this has to do with a spring. So some weight or force. Think of a weight. Spring constant. And S is your how long it gets, right? If you stretch something so long, what weight will be at. So how long the spring gets. Okay. For example, if you have a mass of 10 pounds and it stretches a spring a half a foot, okay, how much would the spring stretch with an 8-pound weight? Okay, so if you have something like this, right, we want to know, okay, how your 10 pounds is going to be your force, right, because that's what's making the spring stretch, is going to equal, well, some constant, right? And usually you do like an absolute value. Don't worry so much about the negative. The negative's there because it is like counteracting, okay? So in this case, it stretches it a half a foot, right? And now if you solve, our constant would be 20. So you would get a function that looked like force equals 20 s, and then we could plug in 8 for the force and solve for how long it would stretch. And in this case, it would do 2/5 of a foot. So you can see the difference when you're putting a weight on different masses. So you need that when you're doing these word problems, because if in our first thing, that value of K, that spring constant, is important. The other thing that we're going to need is mass. So we all know, like, Newton's, well, maybe you don't know that it's Newton's second law, but you probably all have heard of this, where weight is equal to mass times gravity. Okay. Gravity in this case, we always want that to be either 32 feet per second squared or 9.8 meters per second squared. And it just depends on if the problem is dealing with feet or meters. The other thing that we would need when we do these problems is we're looking for mass. So weight really is the same thing as force above, right? So, these two things are the same. And so this is, you're thinking pounds here. Mass, right? We want to get that into slugs, kilograms, etc. And I already talked about the gravity. So this is another value that we want to use as well. And I'll show you how to use that once we get, like, if you know the weight, for example, like here, how much mass? 10 pounds, right? So you would do 10 pounds. Oh, my bad, I said 10 pounds. So 10 pounds over gravity, and let's say it's in feet, we would divide by 32, and that would be your mass, okay? So it would be like that, where you would have, I did that too fast, where the 10 pounds equals the mass times 32, right? And then you would solve, and that's how you would get that 10 over 32 for how much mass it is. So let's do our first problem. Okay. So here you have a mass weighing, whoops. Okay, so here you have a mass weighing 2 pounds, stretches at 6 inches at T. So Y of 0 is released. It's at a 0.8 inches below equilibrium. Okay, so if you think it's below equilibrium, and I'm going to change it to feet just because that's in feet. Let's say it's 2/3, right? So 8 over 12, so 2/3 feet. And then it says below the equilibrium, so there are equilibrium here as an upward velocity. So y prime of 0 is going to be upward, is going to be negative. So that's negative 4.3 feet per second. Okay, and the reason why it's negative is because the distance between like the top of the spring and where the equilibrium is getting shorter. If it was going down, it would be positive, so you got to think of that. So to determine the equation of motion. So again, when you see a problem like this, and if you notice this, we are just talking about a free undampened motion. Okay, and the reason why is there's no other force acting on it. So there's, besides gravity, we don't have anything else really acting on this. Like there's no motor, there's no force, there's nothing else acting on it. Okay, which is not very true in the real, in real life, but these are just easier problems that we could do to get the hang of this. And also it's just solving the differential. So when you see this, it's going to now be x. They want you to use x, but if you use y, it's all right. Just be careful when you plug into the problem. So you have the second derivative, and then you have that w squared, right? X equals 0. And in this situation, this w squared is equal to k over m. So really, I don't really even use that. I'll just put this as k over m, meaning that spring constant over mass. And then x equals 0. And then you could see we have a type of differential that you want to use here. Okay, so in our situation, if we know that you have a weight, so force equals ks, so a weight of 2 pounds. Now since I'm in feet, if you notice I'm in feet for all of these, 6 inches, right? I'm going to change that to feet, so k times that 1/2 of a foot, so I get 4 to be k. And now I also want to find what my mass is. So remember, if you're doing this, W is equal to mass times gravity, right? And here we have weight would be 2 equals the mass times, and since we're in feet, I'm going to use 32 for gravity, so I get 1/16 is my mass. All right, now all I'm doing here is just taking the values that I got for K and I got for my mass, and I'm just plugging them in here. So I'll have x double prime plus 4 over 1/16 x equals 0. And then here you go back to when we were solving with just constant coefficients, the homogeneous with just constant coefficients, and then we could write this as m squared plus 64 equals 0. So I know m is going to be plus or minus 8i. And now I could rewrite my equation. So remember, this is x of t equals c1 cosine 8t plus c2 sine 8t. And just be careful of the 8, okay? I mean the t, not the 8. The t, because they might mark it wrong on the web assign. All right, last steps that you're going to have to do is go back up to your initial values that are given. So here, I don't know why I didn't put that, don't put that over here. If you want to take the derivative as well, negative 8c1 sine 8t plus 8c2 cosine 8t. So I know if the initial value is starting 2/3 away from equilibrium, right? So I'll get 2/3 equals c1, and then plug in, I'll get negative 4/3 equals 8c2, so c2 has to be negative 1/6, and now we have an equation for this motion. 2/3 cosine 8t plus negative 1/6 sine 8t. And there you go. And then, you could use this to find out where the spring is at any given time. Okay. The second example that I want to do, (5.12). Okay, this is free. Now there is some damped motion. Okay. And you'll see what I mean by that in a second. So here you have the new notation is going to be x double prime plus 2 lambda x prime plus this w squared x equals 0. And here, again, there's notation for you. 2 lambda is going to be this damping constant over the mass. And I'll explain when you see a problem what that is. And we still have the same thing for w squared, which is just the spring constant over the mass. Okay, so we could just write it out as, b over m x prime plus k over m x equals 0. I like that better. And like I said before, b is going to be a positive damping motion or damping constant. And we already know m is the mass and k is our spring constant. Okay, so let's bring up the next example. All right, so here we have a mass weighing 8 pounds that stretches a spring 2 feet, assuming that the damping force numerically equals 2 times the instantaneous velocity. So anytime you see that constant, it's going to be related to the instantaneous velocity. So it's how the force is related to the instantaneous velocity. So in this case, b is going to be 2 because it's 2 times that. If it's equal, it would be 1, and so on. So determine the equation of the motion if the mass is initially released from equilibrium. Okay, so that's pretty straightforward. So x of 0 is going to be 0 from equilibrium position with an upward velocity of, so x prime, because its velocity of 0 is going to be upward negative, so -3. So this is what's given to us. We also know that force and the weight, right, is 8 pounds this time. And we also know that S is going to be 2. So let's find K. So remember, force equals Ks. So here we have 8 equals K times 2. So K is going to be 4. And mass. And then the mass, right, so weight is equal to mass times gravity. So we have 8 equals m times 32, right? We're talking about feet. And m would be 1/4. So now, let's take everything we got, right? So you have K, you got M, and you got your damping constant. So we'll have X double prime plus 2 over 1 second. Sorry, let me just see something here. Oh, yeah. I was going to put 4. It's 1/4, sorry. And then over the mass, which is 1/4, plus 4 is K over 1/4. Don't forget your derivative and your function equals 0. Okay, great. So now we got X double prime plus 8x prime plus 16x equals 0. And here we go back to solving a homogeneous equation with constant coefficients. So we could go to m squared plus 8m plus 16 equals 0. So m squared plus, my bad, not m squared, m plus 4 squared equals 0. So we know m is equal to -4. And this repeats, right? Repeating. Okay, so you're going to get an equation that looks like x of t. I don't know why I wrote it like that. X of t equals c1 e to the -4x plus c2, remember it repeats, so you add an x, e to the -4x. So that's what we have here. Now going to our initial values, we have initial values of where it starts at equilibrium and its velocity was going up -3. So let's take the derivative first. And we're going to get -4c1e -4x plus c2e to the -4x minus 4c2x e to the -4x. All right, let's use what we got, right? X of 0 is 0, x prime of 0 is -3. So if we plug in 0, set it equal to 0, we're going to get c1 to be 0. And then same thing, so you'll get -3 equals -4c1 plus c2 minus 0, right? So you get c2 equals -3. So we get an equation for this as -3 x e to the -4x, and there's your equation. All right, not bad.